In 2022, the world got a very cool new bridge. Two bridges, actually. The Iowa-Illinois Memorial Bridges carry Interstate Highway 74 over the Mississippi River between Moline, Illinois and Bettendorf, Iowa in the Quad Cities area. It's a gorgeous pair of structures with the basket handle arches carrying each deck over the main span of the river. But even after they were finished, Iowa DOT had a problem. The two old bridges were still right there, also crossing the Mississippi River. And even though they were kinda cool looking, they just couldn't stay. The bridges were already in poor condition, and without extensive ongoing maintenance, they would continue to deteriorate, posing a danger to the public, affecting the sensitive environment along the river, and even disrupting this critical shipping artery. The old bridges would have to come down. Demolition, on its face, seems kinda easy. For a billion-dollar bridge replacement project, the demo part feels almost like housekeeping. Smash the structure down or blow it up, then just pick up the pieces, no engineering needed. The truth is that it's anything but. Demolition engineering in many ways is even more complicated than designing a new structure, and the I-74 bridge is the perfect case study in why. And don't worry, there are explosions at the end. I'm Grady, and this is Practical Engineering. The original I-74 bridges, with just 2 lanes each, were way overdue for an upgrade in capacity. This is actually a problem they faced and managed to overcome once before, many decades back. Despite looking like twins, the original pair of bridges were built a generation apart. The first span was completed in the mid-1930s, but car ownership and traffic exploded after World War II. Engineers decided that the best way to increase capacity was to build a nearly identical bridge right next to it. That new bridge was opened in 1959. Neither bridge was ever intended to meet interstate standards. They predate the interstate system altogether. And yet they found themselves carrying interstate levels of traffic way beyond what the designers in the 1950s, and especially the designers back in the 1930s, had considered. The lanes were narrow and there were no shoulders, so they required a lower speed limit, which bottlenecked traffic on I-74. Size isn't everything, though. The bridges were also just physically wearing out. Like an old car, it eventually got to the point where the cost of replacing the bridges was outweighed by the constant maintenance and threat of disaster. In 2012, Transportation Secretary Ray LaHood toured this structure, reporting back that it was, quote, "one of the worst bridges I've seen in America." You would think that already being close to falling down would be to their advantage when it comes to demolition, but it's quite a bit more complicated than that. These were big bridges with 3 types of structural designs. There's these 3-span continuous truss units over the old, non-navigable part of the river. There's the deck trusses that kind of act as connectors, and then you have the big 3-span suspension section. I'm sure you want to see the explosion, and I promise we'll get there, but it's basically the last step. Of course, there are lots of cases where it makes sense just to blast a structure down right away. You end up with a pile of rubble that you can manage with regular construction equipment. It can be much quicker, easier, and safer than dismantling a structure piece by piece, but it's rarely true for bridges. Of course, you've got the water that complicates things. Removing debris from below the waterline is challenging. Long-reach excavators can sometimes handle the smaller stuff, but you often need divers to rig the big stuff to be lifted out by cranes. That's dangerous and difficult work. You also have shipping traffic to consider. This stretch of the Mississippi is a busy part of the inland waterway system, and closing it to clean debris out of the channel is a disruptive task. The other thing making it tricky in this case is the environment. There are endangered mussels living in the non-navigable channel below the continuous truss spans, so the demolition team couldn't use blasting or even temporary supports in that part of the river. The only option was to dismantle the bridges more carefully and thoughtfully. Step 1 was to get the deck off. The strategy here was to saw cut all the concrete into pieces small enough to move with construction equipment. An excavator with a slab crab attachment could lift each panel off the steel structure, swing around, and pass to a wheel loader to carry it off the end. Sounds simple, but it had to be done pretty carefully. Cutting the concrete into panels like this means that the reinforcement is cut too, and this is just a cool part of demolition engineering, using calculations and analysis not to design something new, but to answer a tricky question like, can these concrete panels support the weight of a 35,000-pound excavator? The answer was more complicated than just a simple yes. So the engineers imposed pretty strict positional requirements for the demolition equipment. In most cases, making sure that the tracks of the excavator were always directly above the stringers instead of relying on the concrete deck panels to act like beams and transfer the weight. Another challenge on the suspension span was asymmetric loading. It's easiest to use the bridge to dismantle the bridge, systematically working your way toward either end. The problem is that if you take all the weight off one section of the bridge while it's still remaining on the other parts, the trusses are gonna bow, the towers are gonna deflect, and you could actually fail the bridge prematurely. It's just like re-racking the weights at the gym. If, instead of alternating, you take everything off one side of the barbell, you might have a bad time. So, on the suspension bridges alone, the deck removal was this multi-stage process. Some slabs were removed with the excavator and loader, others were popped up and left in place as counterweight to be removed by a crane later. It's a lot more work with a crane, and slower, but it was the only way to get the deck off in a symmetrical way to avoid overstressing any part of the bridge. Once the concrete deck was off, the contractor could start removing the steel trusses, beams, and stringers that make up the bridge structures. And this gets pretty tricky too. You can't just go cutting up a bridge willy-nilly. This is like Jenga on hard mode with very high stakes, and that requires some structural engineering. On the continuous truss section, the demolition team wasn't allowed to install temporary supports to avoid disturbing the muscles. So instead, they floated in support on a barge. This allowed them to safely cut the trusses into pieces small enough for the crane to handle without causing a collapse. The suspension spans were even more complicated. You can imagine how dangerous it is to cut a piece of steel that's under significant stress. As soon as the member is severed, it could cause sudden movements and load redistributions within the bridge. Those cuts have to be carefully sequenced. When you're actively weakening a structure, each step changes the stresses, shifting them around and altering their magnitudes and directions. You have to check each step before you do it to make sure it's not going to endanger workers, ships below, or the environment, and there's no way to know how much stress is in a member just by looking at it. Instead, they had to create a structural computer model, but that's not as simple as recreating the bridge in 3D. The order also matters. One cool example of this, the rivets in the connections for the top chords of each truss weren't installed until after the concrete deck was poured. So most of the load was being carried in the bottom chords in tension. When they removed the deck, the whole truss responded by going into what engineers call negative bending. The top chords were in tension and the bottom chords in compression, the exact opposite of what you would expect. That's something that could have derailed the demolition plan without having gone through the exercise of modeling the bridge exactly how it was originally constructed, modified, and retrofitted over the years. It was almost half engineering, half a history exercise. The engineer even used old magazine articles to understand exactly where those stresses would be. Here's another tricky part. To lift the truss sections off the suspension bridges, they had to put a crane on a barge. Anyone who's been on a boat knows that they're not the most stable platforms for high-stakes, high center of gravity work, especially when you add in the huge loads and the need for precision. They did it for the original construction of these bridges, but that doesn't mean it's easy. Operating a crane from a barge involves dynamic loads from lifting and swinging. Barges often use these spud legs to help keep them in place, but there's still a lot of engineering that goes into checking the stability of a barge for the variety of loading conditions. Those calculations help you pick the right crane, its configuration, limitations on pick weights and movements, etc., to make sure the work can be done safely. And just like the concrete deck, these truss segments had to be removed in a staggered manner to help keep the towers from deflecting too much in one direction. Interestingly, sometimes to demolish a structure, you have to add parts first. The original lateral load system had to be removed because of how the bridge would flex during demolition, but the engineers didn't want people working on a bridge with no way to withstand the wind loads. So they had to design and build these steel bumpers that could transfer lateral loads from the superstructure during the demolition process. In another case, they had to install bearing restraints on the trusses of the continuous spans, again to manage wind loads during the time those trusses were partially demolished. And in another example, they had to build an entire stiffening truss made from pieces of the bridge that had already been removed, so the last deck truss could be lifted and removed as a single piece. All this steel was brought to a location on the shore where it could be cut down using this hydraulic shear and then sent off for recycling. At this point, basically all that was left of each bridge was the suspension towers and cables. Since those cables are essentially one long structural member, there's really no way to safely cut them loose. Imagine getting snapped by an enormous rubber band. There's a lot of stored up energy there, and you don't want any humans nearby when they come down. This is where the explosives come in, and like every other part of the process, this is trickier than you think. Explosives used for demolition aren't really like the ones you see in movies. You're not trying to use them to blow everything into tiny pieces. On buildings, you get a lot of breakup anyway because of the kinetic energy of falling, but really the explosives are just strategically severing columns and beams quickly to start the falling process in a more controlled way. On a bridge, usually what you want is big pieces that can be easily removed from the water. So the explosives are more like small, very exciting saws that can cut quickly, simultaneously, and remotely. Demolition contractors use shaped charges that sever structural members in a relatively controlled manner, and more importantly, a specific location. It matters a lot what these pieces look like after the blast. They have to be small enough to be lifted and transported out of the water, and you want them to fall in specific locations where they're accessible without blocking the navigation channel. So before the explosives are placed, there's an entire process of pre-cutting. The goal is to reduce each location where explosives will be placed down to flat plates or smaller sections, so the blasts are sure to completely cut through. A worst-case scenario is an incomplete explosive demolition that doesn't fully bring the structure down. When that happens, the whole process becomes much more dangerous and difficult because you have to finish the job using workers on a structure where it's not entirely clear where the stresses are or where it's safe to cut. On the I-74 bridges, workers cut the outer strands of the main cable, leaving only 7 of the 37 strands holding. This was done in 4 locations on each cable to break it up into manageable pieces. The towers were also cut in strategic locations to allow the shaped charges to sever completely and control which direction they would fall in the water. And by the way, this leaves the bridge extremely vulnerable. You're basically marching right up to the line of stability so that the explosives can kind of carry you over the finish line to bring the structure down. But it means the clock is ticking. You're checking the weather, working long shifts. You don't want a storm bringing the bridge down before you get to push the button. But once you do, I've mentioned a lot of pros and cons of explosive demolition, but there's one thing they do better than anything else: the spectacle. You just can't get around how cool it is to blow stuff up. They got perfect shots for both bridges, bringing them down safely so the barges could come out quickly to pick up the pieces. The road and navigation channel only had to be closed for a short period of time. Here's a good look at how clean the cuts are from the shaped charges on the cables. And actually, they used explosives to demo the substructures later on. The piers and the more sensitive areas were taken out using conventional jackhammers as the final step. These sheet pile containment structures kept all the debris from spreading out in the water, and of course they did a scan to make sure all the debris was picked up. It turns out one of those piers had become great habitat for those endangered mussels, so you can still see it standing next to the new bridges. But other than that, there's almost no sign those old bridges were there at all. I don't just love bridges. I'm actually a licensed engineer, and part of that means every year I have to take a certain number of classes to stay current in the field. And that's how I first heard of this job. Some of the engineers and contractors put the story together in a professional development class. So huge thanks to them for sharing so many interesting details of the project. And another thanks to Iowa DOT, who answered our questions and shared photos and videos. I am so impressed with this bridge demolition. No shade at all to the new bridges, but honestly, I think taking the old ones down was the coolest part of the entire replacement project. Bridge demolition is specialized, challenging work that takes a lot of engineering to get right. Hats off to the entire team on this project for getting it done so safely and efficiently. You know, I was super interested in that sonar scan they did of the Mississippi River to make sure they got all the debris off the bottom. And really, I love any situation where you get to peer into the details of something that would otherwise be hidden from view. My friend Brian at the Real Engineering channel took that idea to a new level with his series, The Anatomy of. He's putting everyday objects and devices into a CT scanner so we can literally see inside them. This is such a cool exploration of what makes up our favorite gadgets, like the spin wheel in the original iPod or the RF shielding in the Nokia 3310. And if you want to check it out, it's only available on Nebula. You probably know about Nebula now, even if you're not subscribed. It's a streaming service built by and for independent creators. No studio executives deciding what gets the green light, no advertisements driving the content into a single style. It's just independent creators making stuff they're excited about with as few barriers and distractions as possible between you and us. My videos go live on Nebula before they come out here, and my practical construction series, where I followed a large construction project from start to finish over a year and a half, was specifically produced for Nebula viewers who want to see deeper dives into specific topics. I know there are a lot of streaming platforms out there right now, and no one wants another monthly cost to keep track of, but I also know that if you're watching a show like this to the end, there is a ton of other stuff on Nebula that you're gonna enjoy as well. So I've made it dead simple. Click the link below and you'll get 50% off an annual plan. Pay just one time, $30 for an entire year's access at go.nebula.tv/practicalengineering. Or if you have subscription fatigue, but you still want to support what I'm doing, you can get a lifetime membership. Pay once and have access for as long as you and Nebula last. If you're with me that independent creators are the future of great video, I hope you'll consider subscribing. Thank you for watching, and let me know what you think.